Can you see the full screen? Perfect. So, first of all, thank you very much for the introduction and for the invitation. I'm very glad to present this work to logicians, so I can have also some technical, we can have some technical feedback. And so I will just start. As you can see, I'm presenting a joint work with Francesca Poggiolesi and Lorenzo Rossi. And in particular, I'm presenting a work concerning the grounding relation, which I will introduce in more detail, but just to give you an idea, is an explanatory relation. So you could see it roughly either as a relation that allows you to construct explanations, what we could talk about rigorous explanations, or as a relation holding between a true sentence or a true formula in our case, and the sentences that could be seen as the reasons why the formula is true. As I said, grounding is receiving quite a lot of attention lately in several areas of philosophy, and in particular, one could really discriminate different notions of grounding, but we will focus on a particular one and on a particular approach towards grounding, which is the endeavor of formalizing the grounding relation by logical calculus. So to analyze in a formal way the formal features of the relation in abstract. And in particular, we are considering the case of first order classical logic. So we are going to formalize grounding in a language with quantifiers, and therefore to define also grounding with respect to existential and universal claim. That's the main aim of the work. And in this context, there is what one could call a mainstream approach to the formalization of grounding, which has been shown to give rise to paradoxes. So we will in particular consider these paradoxes for this mainstream formalization of first order grounding. We will briefly motivate a different approach and present a calculus following this second one and show that the paradoxes don't arise for this second approach. So I will begin, as I said, with a bit more detailed introduction to grounding in general. By now I'm not committing to a particular notion of grounding, just giving you an intuition about the relation. So grounding is usually presented as an objective explanatory relation, which is non-causal in nature. So as I said, explanatory is related to the fact that ground is supposed to connect, one could say, a truth and the reasons why, or some reasons why the other sentence is true. And we talk about objective explanation in the sense that we're not analyzing subjective features or notions of subjective understanding or of an explanation in a more epistemic subjective sense, but we're really trying to capture a notion of objective reason by such a relation. The specification that grounding is non-causal, I hope it will be clarified by an example that I will provide later, but in general, the idea is that grounding explanations are supposed to be disjoint with respect to causal explanations. So we're not talking about causal connections between events, but we're trying to get closer to a notion of reason, a more, right, one could say more abstract notion of explanation. Now, some terminology. For us, grounding is a relation between two truths. So in general, true sentences, we'll talk about true formulae. One is called the ground, the other the consequence. And in philosophy, there are different kinds of terminology to express grounding claims. In general, the idea that the ground is supposed to determine the truth or explain the consequence. As I said, one could talk about reasons. So the ground in that case would be the reason why the consequence holds. And often, especially in the metaphysical area, they use also the expression in virtue of to talk about grounding. In that case, would be the consequence that holds, obviously, in virtue of the ground. Generally, not always, but almost universally, grounding is regarded as an irreflexive and anti-symmetric relation. And there are clearly connections with the explanatory nature of grounding. In particular, irreflexive means that nothing should be a ground of itself, right? You're thinking about explanation, you wouldn't want to allow someone to explain something just by stating it. And antisymmetric just means that if A is a ground of B, B cannot or should not be a ground of A. And here the idea is to avoid circular explanation or similar problems. Now, I'll just give you a few examples to give you the idea of different areas in which we can apply grounding, and then I will move to our particular approach and talk about formalization. Now, here you can see just a few examples. I'm not committing to the specific example. Obviously, there is also an interesting philosophical work in discriminating what is a genuine grounding example, and just giving you the idea of possible ways of using grounding. Here I use the expression because to express the grounding claim just for simplicity. So we could have sentences of the form, for example, this is a vixen because this is a female fox. In this case, we could have what one could call semantical grounding, right? Related to the meaning of expressions. We could have more factual grounding and say something like Xantippe is a widow because Socrates died, right? We cite a sentence related to a fact to explain why a sentence is true. Or we could have also grounding in physical or in other natural sciences. For example, we could say these two bodies attract each other because of the law of universal gravitation. So in general, a law is not considered as a cause of a fact. In this, here we have what I was saying about the connection with causality. At the same time, a law could clearly be part of an explanation of why a fact happens in physics or in other physical sciences. So one could talk about a grounding connection here, right? And say the law is not a cause, but is still a ground. It can be used in an explanation with the different role. We could also have grounding in more formal contexts, and for example, say the set containing Plato, right? The singleton containing only the object Plato exists because Plato exists, or more in general, that the existence of the element of a set ground the existence of the set itself. This could also be seen, by the way, as a metaphysical grounding case, depending on the metaphysical theory, but certainly some sort of formal grounding in a, I don't know, set theoretical context. Right. Now, the particular endeavor we are considering here, as I was saying, concerns the formalization of grounding or of the formal features of the grounding relation by logical principles or logical rules more in general. We will consider a proof theoretic approach, and therefore we will use logical rules. And in this context, there is a quite extended literature. No, first, let me say the idea of logical grounding, just to give you, is not a definition at this level, but just an intuition of what do we mean by a logical ground, is that if we should consider a true formula F, and the ground of such formula F should contain formulae G1, Gn, such that the truth of F is determined by the truth of the formulae G1, Gn. Or we could say F is true in virtue of the truth of G1, Gn. This is the idea. And in this context, we have a quite, as I said, vast literature referring to what one could call a mainstream approach to the formalization of grounding. Here I quote three authors. It's not really an official research line, but more a set of different authors and works sharing the main intuitions. I quote here, for example, Schneider, Fine, and Correia. And this, we could say, mainstream way of formalizing grounding is related to a particular notion of grounding, which is called, often referred to as full grounding. I will say more about full grounding as well. But just to give you an idea of a grounding rule, so to see how to read the grounding rule, what's the intended meaning, and to already give you an example of a rule related to this way of formalizing grounding, let's have a look for a moment at this rule that you can see here at the bottom of the slide, which is a grounding rule for the existential quantifier. So the way to read this rule is the following. The premise corresponds to the ground. We might have more premises. In that case, the ground is a set containing all the premises, essentially. And the conclusion is supposed to be the grounded formula, so the consequence in our terminology. Another way to read the rule in more explanatory sense is that the premise is supposed to explain the conclusion. Now, let's have a look at the rule. What we are saying here is that in order to ground an existential claim, so a claim of the form there is an x such that f of x, so there exists something which is f. We can use any instance, any positive, obviously, instance of the formula, right? So we're saying, in a sense, if we consider this mainstream formalization of grounding, that the explanation of the reason why the existential claim is true, the reason why there are f, is that a particular object is an f. Just to give you an intuition, we could have the existential claim that is, there are even numbers. The explanation would be something like 16 is an even number. In general, let me stress that an almost universal, possibly universal requirement with respect to grounding rules is that the premise should be simpler than the conclusion. This will be important later. And as for the, we could say, the induced notion of grounding, the notion of grounding induced by this rule, I would say that one could already have some vague intuition that is quite liberal notion of grounding, or at least of explanation, in the sense that saying that any instance, any positive instance of the existential formulae explains the truth of the formula, could be really seen as a rather weak notion of explanation, right? If I say, why are there even numbers? Saying because 16 is an even number might seem a bit loose. But to be fair, the rule is quite intuitive and simple. And that's, in any case, that's the rule that, that is employed in this context of rule grounding. Now, apart from intuitive considerations, there are actually some technical serious problems with the rule, which have been discussed in 2010 by Kit Fine. And in particular, he showed that if we define a grounding calculus following the notion of full grounding, or this mainstream approach, and in particular, we have a calculus containing the existential rule that I showed you, then for very simple and natural extensions of the calculus, we have some serious paradoxes precisely concerning grounding. Now, Fine presents different paradoxes, both for the existential and for the universal quantifier. What I did here was to just pick one, a sort of simplification of one of these paradoxes, just for the sake of clarity. And let me stress before talking precisely about the paradox that here I talked about simple and natural extensions of the grounding calculus, in the sense that we're not considering very ad hoc definitions of extensions precisely aimed at falsifying or finding paradoxes, but Fine considers in general very natural extensions of the grounding calculus, natural in the sense that just give us the possibility of studying the interrelation between grounding and very tightly connected notions such as truth. Here we are going to consider truth theories, for example, or theories about facts. So the problem seems very serious, because obviously if we are formalizing grounding, we also would like to have systems to formally analyze its relationship with cognate notions and similar things. So let's have a look at this version of Fine's paradox. What we are doing here is extending our grounding calculus by a truth theory, very simple one. So essentially we add to the language a truth predicate T, where T of X just means intuitively X is true, and a quotation mechanism for formulae. We don't care so much about the technical details concerning quotations. The idea is just that we can take any formula F, quote it, as you can see here with the angle brackets. I'm sorry, can you see the mouse cursor? Okay, so possibly I'll use it one, right? So we can quote any formula like this. And the idea is that if we do so, we can construct formulae of the form T of quotation of F, which can just be intuitively read as F is true, right? So a very simple truth theory. Obviously, since we add an interpreted predicate in our calculus, which is T, we also would like to have a grounding rule for T, because in general, in grounding calculi, the idea is to have one rule for every logical constant or special symbol in such a way that we can really provide grounds for formulae of any form. So we also add a grounding rule for the truth predicate, which is quite intuitive and rather an obvious choice, I would say. This rule is just telling us that in order to explain the formula F is true, we just state F, right? So essentially this is saying the formula F is true holds because F holds, right? A rather obvious choice. But already with this, we have a rather direct and serious paradox. Indeed, we can consider the formula, there is an x such that T of x, which we could read as there's something which is true. And first of all, quite clearly, we can use this formula to ground the formula. It is true that there is something which is true, as you can see here in the rule application on the left, and by our grounding rule for the truth predicate. At the same time, since there is something which is true is an existential formula, we can also apply the grounding rule for the existential quantifier and provide a ground for this formula. Now, since the grounding rule related to the full grounding approach allows us to pick any instance of the formula, of the existential formula, to ground it, we can just take the old formula, quote it, and use that term, the obtained term, in order to construct the instance. So in particular, we are grounding the formula, there is something which is true, by the formula, it is true that there is something which is true, as you can see here in the rule application on the right. And now we already have a paradox, right? Because the two are grounding rules, right? The premise of one is the conclusion of the other and vice versa. So we have directly a symmetric instance of grounding. So the two formally ground each other, essentially. And moreover, if we are considering a transitive notion of grounding, which is often the case, we also have a reflexive instance. Each of the two formally ground itself by transitivity. So by looking at this particular paradox, we could say that if we want to say that the thesis of our work, or at least the motivating idea, is that the problem with this paradox is essentially related with the liberality of the existential rule for the, the grounding rule for the existential quantifier. So we will essentially introduce a different notion of grounding, stricter than the one corresponding to full grounding, and in particular, according to which the grounding existential rule is really too liberal. We will briefly motivate this different approach and show that by defining a calculus according to this stricter approach, we can avoid and prove that this kind of paradoxes cannot be obtained, are completely avoided by the approach. So in order to do so, we will essentially, I will use to motivate the choices concerning the particular way of formalizing grounding that we are using by citing Bernard Bolzano, a Bohemian and mathematician and philosopher that extensively worked on a notion which is very similar to grounding. In German, he called it Abfolge, which could be translated as consequence, but nowadays is directly translated in grounding, and indeed even theoretically could be considered as extremely close to the modern notions of grounding. So I will show you a few remarks by Bolzano just to give you some intuitive motivation for some requirements that we are going to use, and then I will introduce formally our notion of grounding. So first of all, in his Theory of Science, main work by Bolzano, in which discusses at length his version, we could say, of grounding, it states that at some point, every distinct ground has a consequence that is at least in some parts distinctly its own. So if we take this, we could call a requirement of a grounding, we could, I would say, quite faithfully formalize it by the sentence that you can read here. So the idea I would say is that if we have that G1 grounds C and G2 grounds C, then G1 and G2 must be the same ground, right? Because nothing in the consequent distinguishes between them. So in a sense, we could say that grounding puts forth a ground uniqueness requirement, right? Which is clearly invalidated by the existential rule coming from the mainstream approach, because in general, for an existential claim, we will be able to have several grounds because we will have, not always, but in most cases, more positive instances. Right, so this is our first requirement. The second one, I'm just giving you some examples. This is not the whole work that was required to define the calculus, but just to give you some connections. The second remark is the following, a bit more complex, but let's try to analyze it. Bolzano says, who does not feel that the connection between ground and consequence is much more intimate than it would be if the mere fact that some of the grounds and consequences are combined in thought, we're supposed to make only one ground and one consequence out of them. So I will propose you the semi-formal analysis that follows. I would say that here Bolzano is saying something similar to what follows. So if G1 grounds C1 and G2 grounds C2, it does not follow that G and G1 together are ground for C1 and C2 together, right? I would say if you try and read Bolzano's statement, it should say something like this. If you're, by the way, if you're familiar with linear logic or some other substructural logics, this kind of inference corresponds to what is called often the mixed rule, right? If the mixed rule, if you've seen it, or if you, or otherwise, is just a rule telling us if you have a sequent A arrow B and a sequent A prime arrow B prime, you can obtain the sequent A prime arrow B prime. So Bolzano is kind of forbidding a similar reasoning with respect to grounding. And I would say a fortiori, since Bolzano is essentially saying in a grounding claim, there shouldn't be just some parts of the ground related to some parts of the consequence and other parts independently related to other parts. We could also infer that we cannot have that if G grounds C, G also grounds C comma D, right? We couldn't just add some independent information to the consequence, because even more seriously than in the previous case, we really have that some parts of the consequence are completely independent from the ground, right? And if we consider this last requirement, we have something that we could call complete determination in a sense, right? So we are saying here that the ground should, by now in an intuitive sense, completely determine the conclusion. We shouldn't be able just to add irrelevant information to the conclusion. Right, later I would call about completeness in a more formal sense, by now just giving you the intuition. Now, following this and other remarks, Francesca in 2016 formalized the notion of grounding that is today known as a notion of complete grounding, which is different from the notion of full grounding employed by Fine, for example, and related to the existential rule that I showed you. And just to give you the main intuition between the difference, we could say that part of the difference, the main part I would say, while full ground induces a notion of ground, which is a sufficient condition for the consequence, plus other requirements, complete grounding induces a notion of ground as a necessary and sufficient condition, plus other requirements. So let's have a look at the formal definition of complete grounding very briefly. And then we will proceed to consider the calculus defined according to this notion. Right, so first of all, for complete grounding, we have a notion of ground, a notion of consequence, and also a notion of condition, of side condition. From the following example, you see why we need this. By now, let's have a look at the formal requirements. We say that gamma is a complete ground of formula A under the condition C, if and only if the following three condition holds. First of all, we have what is called positive derivability. So A should be derivable from gamma. Here we have, this is related to the notion of sufficient condition, obviously. But then we also have a further requirement called negative derivability. In this case, we are saying that a kind of negation of A, I'll say a bit more by now, the small bottom on the right, just consider it as a kind of negation. The negation of A should be derivable from the negation of the ground plus the condition C. And here we have a sort of necessary condition requirement, right? Because negating the ground allows us to derive the negation of the consequence. Moreover, we have some conditions on the complexity. As I said, often logical grounding requires some notion of simplification to be valid between consequence and ground. In particular, the ground should be simpler than the consequence. In this case, we use a refinement of logical complexity, and I'll give you a few intuitions later. But the idea is simply that the condition and the ground together should be less complex according to this notion than the consequence. If we are considering immediate ground, as we will in the calculus, we have that the consequence should be one step, 1 point more complex than the ground. Now, a few words just to give you the intuition about the complexity we are using. In a sense, we have a requirement of logical complexity because We consider logical complexity, but to count the connectives, we also consider that grounding is a sort of positive truth determination relation. So we have problems with negation. The simple intuition is that if we consider a formula of the form not P, P will never be a ground of not P, because P will never positively, the truth of P will never positively determine the truth of not P, right? So just in brief, we have to handle negation with care. And in G complexity, we do it in a sense, ignoring individual negations. So a double negation is treated as one connective in a sense. And if we have a negated conjunction, we just consider it one more point of logical complexity and something similar. Now I can also briefly explain what the kind of negation that we are using is doing. Essentially is a way of negating formulae that preserves logical complexity. So in a sense, you add the negation if that doesn't increase the complexity, or you remove the negation if that doesn't decrease the complexity. But it's essentially just a way of talking about something equivalent to the negation of the formula. Right, this is a brief formal sketch of how complete grounding is defined. And now I will show you the propositional part of the calculus, just to give you a simple idea of how the proof theoretical rules work, and then we will move to the actual focus of the presentation, which is the quantifiers. Right, so we can look for a moment at the grounding rule for the conjunction, which is very simple and just allows us to get into the subject easily. I'll also stress that we denote in the following by a double inference line grounding rules to distinguish them from logical rules. Now, if we look at the rule, the grounding rule for conjunction is quite simple. It's actually the same also for the full grounding case. In particular, we are saying that in order to explain a conjunction A and B, we take individually each conjunct together. So individually without the conjunction connected, but together. So the ground of A and B, of the formula A and B, is the formula A and the formula, contains the formula A and the formula B. Clearly, we have a complete determination. It's quite obvious to see. We are simplifying the logical complexity by going to the premise, and we have that. If we consider for a moment also disjunction, that gives us a more interesting case. If we are considering a notion of complete grounding for disjunctions, we have a bit more subtle. In particular, first of all, if both disjuncts A and B are true, we must cite them both in the ground, because as I said, we want the complete reason intuitively why the disjunction is true. So if both disjuncts are true, both A and B are in the reason why the disjunction is true. In case only one disjunct is true, as for example, here we have A is true, B is false, because the converse of B is true. And then A is a complete reason why the disjunction is true, because B is false, right? So the whole reason is A, but we must specify this. And here we have that the side condition comes into play. So essentially the rule is saying A is the complete reason why A or B is true, considering that B is false, right? In a sense, so we have the ground is only A, because B doesn't, we could say, positively determine the truth of A or B, because, well, the converse of B is true, so B is false. But we have to cite also the condition, right? This is roughly the idea for the propositional case. Here we have double rules considering positive and negated connectives, just because of the considerations that I talked about, but there is also a way of treating negation in a unified way. This is just a bit simpler to present, so I'm considering this. Now let's have a look at some considerations concerning the quantifiers.
Can I ask a question?
Absolutely, yes.
Maybe you mentioned this and I missed it. What is the vertical line there?
So right, sorry.
The second
yes.
disjunct, what looks like a disjunction introduction. How is the second one different from?
Right. No, I didn't mention the symbol. That's to discriminate between the ground, which is to the left, and the condition. So essentially, in a rule with the bar, you have that the ground is a premise, and the condition is put aside by the bar, essentially. So to the right of the bar, you don't have part of the ground, but you have the condition.
But is it something like the conditions on existential elimination in standard natural deduction, for example?
No, it's just the condition is part of the formalization of the grounding relation. So it's just, this is just a visual device to know that when you apply the rule, the ground is only the formula on the left.
Okay, thanks.
So in a logical derivation, both premises are normal premises, but if you read it as an explanation rule, you know that to the right of the bar, you don't have a part of the ground, but you only have side condition. Okay, should I proceed?
So, sorry, Francesco.
Yes.
Just another follow-up on this. This condition, what does it mean? That you have to have been proved, or a condition that is assumed?
No.
So technically speaking,
it's a normal premise.
It's just a premise. So
it's just a premise. Yes.
So an assumption.
Yes, it is. If you see the grounding derivation, I will show some examples.
Thanks.
If you see the grounding derivation as a logical derivation, also using stronger rules, it's just an assumption. The bar is only used when, as you will see, you introduce the grounding connective. So it has a meaning only with respect to the rule read as an explanation rule. From a logical point of view, it's just a normal premises. No problem. Right. So a few considerations on the existential rule. So as I said, we would like intuitively to capture a notion of complete grounding, right? So we would like to have a unique premise and a premise that completely determines the truth of the conclusion. Now, this is not very intuitive from a proof theoretical point of view, because we are often used to think of existential claims as verified by particular instances, but actually in the literature, there is a device that allows us to really capture the full, to completely capture the truth of an existential quantifier. And this is the Epsilon symbol. Now, very briefly, the Epsilon symbol has been introduced by Hilbert to define the behavior of quantifiers, we could say, without using quantifiers. And it's just an operator that takes, we could say, takes as an argument a formula with a free variable f of x, and allows you to construct a term, epsilon x f of x. Intuitively, this term is a term, so we can apply predicates to it, and in a sense is a sort of quotation mechanism as well. And this term, epsilon x f of x, could be seen as a name for an indeterminate object enjoying the property f. So you could read epsilon x f of x as some indeterminate object enjoying the property f. Now, the logical properties of epsilon terms are quite simple. We can show that the property f applies to epsilon x f of x if and only if at least some object enjoys f, right? So we could say meaningfully talk about the indeterminate or an indeterminate object enjoying f only if f actually has objects, corresponds to objects enjoying it. And in case we have at least one object, when we talk about the indeterminate object enjoying f, we know that it actually enjoys f. So from a logical point of view, if you have an example, a specific example f of t that you can show, then you can introduce the epsilon symbol and you're guaranteed that f holds for the indeterminate object enjoying the property f, right? It's quite simple. You can see the introduction rule proof theoretically here. Now, by using this, and I'll stress, you can axiomatize the behavior of the epsilon symbol by the sentence, by formalization of the sentence that you have in this slide. Now, by using the epsilon symbol, we can define the grounding rule that you can see here, right? So what are we doing here? We are saying the ground of an existential claim of the form there is an x such that f of x is the formula f holds for the indeterminate object enjoying f. So from a technical perspective, we have that the premise is unique with respect to the conclusion. We have a logical simplification because we are removing essentially by going upwards the existential quantifier, and we have full determination because if you negate the premise, so you say the indeterminate object enjoys f doesn't, not even, right, we could say the exemplar object enjoying f, not even that object enjoys f, then you can imply that nobody enjoys f. And we obviously have, it's a sound rule, right? So we have positive derivative. Now, from an intuitive point of view, to be fair, the intuitions are a bit abstract here because we are talking about pure logic, but you could say that you forbid to explain an existential claim by committing to a particular example, right? You cannot you cannot give a specific example and pick it arbitrarily as the ground of the conclusion, but you have to keep your example abstract in a sense. So the epsilon object really allows you to abstract the witness for the formula F from a specific witness to a more generic abstract example that verifies the existential claim. There is also a slightly, we could say, pragmatical intuition about the epsilon object. You could also read the premise as follows. Since epsilon objects are formalized by choice functions, you could also say that to explain why there are objects enjoying F, you say that if you look for an object enjoying F, you will find it and you will be able to prove that F holds for it. Just some looking at the semantics, you might have this more procedural interpretation. Right, a few words about the universal rule. How much time? I still have 10 minutes, right? If I'm not mistaken. Okay. A few words about the universal rule. So if we consider the context of full grounding, we have that often rules for the universal quantifier are defined according to the idea that in order to ground a universal claim, you should use a possibly infinite list of sentences stating for a list of terms of constants C1, C2, C3, stating that F holds for every element of this list, right? So the idea is you take an possibly infinite list that names every object in the domain, you prove that F holds for every element of the list, and then you can ground the universal statement. But if you're considering arbitrary domains, this is not true. So it's not enough to have an infinite list, even if it really names every object in the domain, and to prove that F holds for every object of the list to imply the conclusion, to imply the universal claim. Because nothing guarantees you intuitively that the list is actually exhaustive with respect to your domain. You could also always have a new object that is not named. So what they do often is add what is called a totality factor, which is the left premise of the rule, the top rule that you can see here, which is simply a formula stating that for every object in the domain, it is named by at least one of the elements of your list, C1, C2, C3, and so on. Now, apart from the fact that here we're essentially saying that to explain a universal claim, you need a possibly infinite list of statements, which arguably could be a problematic, right, choice for epistemic reasons. But actually, we also have more technical problems, or possibly more serious technical problems, concerning the totality factor. Indeed, the totality, if we think about simplification, right, the idea is that the consequence should be simpler than the premises. Here we have an infinite formula, right? Not only the premises are infinite, but actually the totality fact is an infinite disjunction and is a universally quantified one, right? So first of all, we have to use infinite error logics, infinite languages, not only infinite rules. And secondly, one should find a way to argue that the totality fact is simpler than the conclusion. The only solution that I found in the literature is to just consider the totality fact as an atom, but that's not really a solution to me. It's more just right, solving the problem by just neglecting it in a sense. So what we did to treat the universal quantifier according to our requirements is related to a very well-established trick or technique used in proof theory, right? So, which is essentially the eigenvariable conditions. So if you want to prove a universal claim in a proof theoretical calculus, what you do often is you provide a universal claim of the form for every x of f of x, for example. You provide a proof of f of x, where x is a free variable, but you also require that in the proof of f of x, you have no assumptions on the variable x, right? In this way, technically, your proof of f of x could actually be seen as a proof of f for any term, f of t for any term t, because since you have no assumptions on x, you can just replace x by t, and you have a proof of f of t. So you prove that for every term t, f of t holds. The problem with eigenvariable conditions for us is that these are proof theoretical conditions. So you, in the premise of the rule, you have a formula with a free variable. You don't really know that it's under eigenvariable conditions. So what we needed to do was to essentially internalize the notion of eigenvariable in the object language in such a way that we can really say the premise is the reason why the consequence holds, right? Without side conditions which cannot be expressed in the language. And in order to do so, we exploited we could say a simplification or an adaptation of Fine's theory of arbitrary objects, which is essentially a way to remove free variables from logics and replace them by constants for arbitrary objects. What we do is add a constant for the arbitrary object, the constant A, which is supposed precisely to denote the arbitrary object. If we do so, essentially, we can internalize eigenvariable conditions and we can define the grounding rule that you can see here. It's very simple. F of A grounds the formula for every x f of x, where A is a name for the arbitrary object, the name for the arbitrary object. Now, the premise is unique. Logical complexity is it's quite easy to see that logical complexity is reduced by going to the premise because we're removing the universal quantifier. And we have also that the premise implies the conclusion and the negation of the premise implies the negation of the conclusion. Because a few words about the arbitrary object, the logical idea about the arbitrary object is precisely that an arbitrary object enjoys F if and only if all objects enjoy F. Now, this is not axiomatizable as a principle. You obtain contradictions, but by working on the semantics, you can actually formalize this notion, and that's what Fine does, and that's what we adopt for our work. From a proof theoretical point of view, to introduce it is very simple. We just prove f of x with eigenvariable conditions referring to x, and by that we can introduce the name for the arbitrary object. Now I have I'll show you the rules for the quantifiers. Here as well, we have the double rules for negated quantifier and positive quantifier. The first two are those that you have seen already. And then just the remark that in order to ground the negated universal, we use the technique related to the existential for obvious reasons. And in order to ground the negated existential, we are using the arbitrary object. So the way we formalize the grounds for the universal quantifier. Now I have, 2 more slides. I still have a few, 2 minutes should be enough. Now, in the calculus, we also have rules for introducing the grounding operator, right? So we can internalize also grounding inside the language, because by now we've seen proof theoretical rules, grounding rules, which provide a metalinguistic, we could say, analysis of the grounding relation. But we also have rules to actually formulate statements concerning grounding in the object language. The idea is quite simple. Since grounding is a very strict relation, we can only introduce the grounding operator immediately following an application of a grounding rule. So if a rule tells you that gamma is a ground of B, given the condition C, immediately after this rule application, you can introduce the grounding operator. And you should read the grounding claim as obvious, right? GR gamma CB means gamma is a complete ground of B given the condition C, right? Here you can see why we have the symbol with the bar. You could do it other ways. Essentially, you just know what to put in the ground and what to put in the condition. It's quite simple. In order to eliminate the grounding connective, we have 2 rules related to factivity. So the idea with the explanation is that when you explain something by something, both things should be true. Right? You explain a true thing by mentioning other true things. So essentially, we can eliminate the grounding connective as if it were a conjunction, we could say, in proof theoretical terms. And simply, we can derive any part of the ground, the condition, or the consequence from a grounding claim. We also have a way to negate wrong grounding claims, to derive the negation of wrong grounding claims. So we cannot derive wrong grounding claims because of our introduction rules, but you could still put as an hypothesis that a wrong grounding claim is true, right? You could say, suppose that F is a ground of F. In that case, we have the rule that allows us to obtain the falsity from a wrong grounding claim. And wrong means in particular that either falsifies the complexity conditions or falsifies, we could say, the completeness condition, right? So if you have syntactical problems in the ground, you can derive bottom, and for example, you can derive the grounding claim is false. I'll also just mention briefly that if you have contradictory formulae among the ground or the consequence, you could just derive falsity by factivity, right? By deriving the formulae and then obtaining falsity in a logical way. All right. Now, I have two examples that I think I will skip because I'm running out of time. So these are technical examples just to show you how to use the rules. But if you're interested, please ask and I can discuss them as well. And I will just conclude with a few remarks about the whole calculus and the paradoxes again. Is there a question? No, okay. Right, so first of all, we can very easily show, it's almost trivial, that in the logical calculus, it's impossible to derive any symmetry or reflexivity paradox or any grounding loop in general, because we have our notion of G complexity that gives us a linear order, well-founded and everything. It's a very simple one, by the way, on formulae connected by a grounding rule. So it's impossible. We can easily show that there is no loop of any sort, nor any reflexive thing which is derivable. But the original problem concerned the truth theory, right? So also a few words about possible extensions of the calculus by a truth theory, like the one you've seen or similar ones. We still have to write down the results, but we already have in mind what techniques to use. And the idea is that even if we extend the calculus by the truth theory, we can still show that no reflexivity of symmetry paradox arise. The intuition is the following. The problem was caused by the fact that you can, in the full grounding existential rule, you can cite the consequence inside the ground, right? Because you can just quote it. You can take any instance, so you can just quote the consequence and use it in the ground, which means that you can construct the ground by citing formulae, which are intuitively too complex for the ground. This we cannot do in our calculus, because when we use the epsilon symbol, the formula we refer to doesn't contain the existential quantifier anymore, right? So we can use the formula epsilon x t of x in our ground, but t of x is clearly simpler than epsilon x. Then there is an x such that t of x. And so the idea is that we cannot produce the loop. Technically, we should, but it's not hard to do, define a complexity counting logical complexity and the complexity of formulae quoted or used inside epsilon symbols. And this can be done easily. There are techniques for truth theories to do so. And if we do that, we can actually show that we have this double level simplification at the level of terms and at the level of formulae that allows us to prove that, should allow us to prove that there are no grounding loops. So this was all. Thank you very much for your attention. And if you have any questions, obviously I would be happy to answer.